be like, hey, the ball would bounce before it would get to them. They'd laugh, right? And then they go, ah, right? And eventually, like Calvin and Hobbes, I'd get like upended by, yes, are you picturing this?
Yes.
Okay, so what you need to understand is that photons are like those red rubber balls for electrons. Okay, and electrons are, right, I mean, when they hit an electron, they change its position or its momentum, yes? Does this make sense? Okay, so two principles. One is that the momentum is h over lambda, and so if you have a big wavelength, you have a small momentum. If you have a small wavelength, you have a big momentum. Yes? Does this make sense? There's a relationship there. The second thing you must understand is if you want to know where I am accurately, if you want to pin down my position, do you want to use a small wavelength or big wavelength? Small wavelengths can pin down the position. Okay? So our uncertainty is on the order of the wavelength. Yeah? Yeah? Okay? And so this is why there is this relationship. Okay? If I try to really find out where the position of some electron is, right? Or any object for that matter, right? If I want to find where it is, I fire a very small wavelength at it, yes? If I want to make this small, I have to put a very small wavelength in there, which means I've got a big momentum. So although I may know where the particle was very accurately, what's happened to its momentum? It's changed by some random amount. I have no idea about the momentum, right? It's like there's this object, and I hit it with a rifle bullet, right? It's like, poof, right? Oh, I know where it was. I have no idea what its momentum is now. Yes? By observing it, I've introduced an uncertainty in its momentum, and I have no idea what its momentum is. Yes? Does this make sense? On some level, right? So there's a weird thing there. This is another weird thing about, and this is Schrodinger's cat, right? Is that observing changes what you're observing. There's no casual sense that I can just sit there and watch and be like, right? No. Observing is interacting. You have to use things to observe on a small level, right? I have to use photons to observe. They might be the least intrusive thing. Just the act of observing it changes it. Yes? This is a strange thing, isn't it? In fact, when you do this whole probability thing, right? What they say is the Schrodinger wave equation, when you observe the electron in a particular place, the wave function collapses. All other things go to zero. Where you observe it is 1. It's like all probability like that, right? Same's true for the cat, alive or dead. When you observe it, well, depends on how you observe it, right? Okay. So this is the notion. I'll just hit the right arrow, right? And so if we want to know the momentum very accurately, what we do is we observe it with a very large wavelength photon. Yes? I don't want to change its momentum, so I observe it with a very large wavelength photon, but now I have no idea where it is, because the uncertainty of my position is on the sides of the wavelength, and the wavelength would have to be large, right? So you can't have both. If you try to observe its position accurately, you change its momentum. And if you try to observe the momentum, then you can't glean information about its position because you're using such a large wavelength. It's like, remember the analogy of me standing in the hall and you throw balls of different size down the hall? I think I wasn't here to make this analogy, but it's a very good analogy, right? Okay, if you throw enormous beach balls down the hall, all you can tell is that there's something in the middle on the bottom of the hall, and you could throw beach balls above my head and a little bit to the side, right? If you use red rubber balls, you discover that there's a space here. Yeah? And there's you can get them through here too, right? Ouch, yeah? If you use soft balls, then you can discover the structure of this arm, ouch, yeah? Right? If you use golf balls, you discover the finger. Somebody gets a PhD for discovering that there's a space there, right? If you use marbles, ouch, right? You can, somebody discovers the little finger and the middle finger, something like that, right? If you use BBs, ouch. Think of all this stuff. You discover the ear. I don't know, right? Yeah. Okay. So this is the notion, right? Is that the wavelength is on the order of what you can discern, right? Okay. There are two Heisenberg quantities too. Okay. There's also energy. There is also energy and time. And so this is an interesting one, right? I thought energy was conserved. Well, strictly speaking, okay, energy is not conserved. For brief periods of time, small objects, right, can get more energy than they would have otherwise, right? So remember, though, that this is an extremely small number, right?
Like theory or
No, this is well accepted, right? In fact, the sun would not be shining today as brightly as it is, if possibly at all, if there wasn't this thing here. This accounts for a lot of the nuclear fusion in the sun, because it's not likely that these positively charged things will get close to each other. They actually have to borrow energy briefly to get close enough to fuse, which is an interesting thing. Radioactive decay. When things radioactively decay, you can show that they don't have, an alpha particle doesn't have enough energy to get away from the nucleus at all, ever, right? So it has to actually borrow energy briefly to escape, and then once it's gone, it gives the energy back, or something like that, right? Okay, so this is a short period of time. Hawking radiation. There's actually particles inside the event horizon of a black hole beyond the point of no return, right? But yet they can escape, and they do that because for a split second, for a short period of time, they gain enough energy to escape, and then once they've escaped, they've escaped. Yeah, it's a very fine line like that, right? Okay, so this is a bizarre thing on the quantum level, on the very small level. Particles can gain energy from nothing, right? In fact, there's a whole theory of particle dynamics that talks about virtual particles coming out of nothing. Yeah.
Particles or electrons like move in wavelengths.
Yeah. Oh, do they go like this? No, not so much. But when we talk about wavelengths with particles, we talk about a probability wave. Yeah. Now, to be sure, you're not going to notice this on a baseball pitch, right? To be sure, I mean, the batters think this happens, right? But the ball doesn't go like, and then suddenly go faster and then go right like that. Because remember, this is like a really, really small number. This is like 10 to the minus 34th. The pitch just looks like it's doing that. You're like, dang, right? But it's not really. You can't. Big objects don't do this. Just small things, electrons, yeah, can do this, and you notice it. It's an important thing for them. Okay, and then I think the second thing you need to understand is when we talked about uncertainty, if it's 3.5 plus or minus 0.2, right? The uncertainty of x is the 0.4, so it's the total range of things. So just keep that in mind for the problems you're going to do tonight. That's the important thing. So 3.5, if it's plus or minus 0.2, the range delta x is actually 0.4. It's like the range of it. And I think there's an example. Isn't there an example problem? Strange quantum effects. We've talked about that. Energy is non-determinism. Yay. Right? And then this final thing here, quantum electrodynamics, is just totally bizarre. But the notion of quantum electrodynamics, for example, if two protons repel, I don't know how to explain attraction with this, right? If these guys are like approaching each other in a vacuum, they're actually surrounded by these virtual particles. In this case, they're photons, okay, that just boil out of the vacuum. Where do they come from? Well, for brief periods of time, they borrow energy from the vacuum, right? And these things mediate the electromagnetic force. And then this works, by the way, if the particles, the Coulomb's law predicts repulsion, yes, right? Quantum electrodynamics works always, even if the particles are moving really fast, right? And so this is actually a better theory. Does that really mean that the vacuum is seething with these virtual particles, none of which have ever been detected? Again, this is another theory of knowledge thing. If the theory predicts better than any other theory, maybe it's right. I don't know. Yeah. This is a strange thing. Okay, so what is the uncertainty in the position of a 0.145 kilogram baseball with a velocity of 37 plus or minus 0.3 meters per second, right? Okay. So I'm going to use this guy up here, the momentum one, because we're talking about position, therefore we're going to talk about momentum. And so all I need to do is figure out the uncertainty in the momentum, right? And the uncertainty in the momentum is mass times the uncertainty of velocity, right? So it's going to be 0.145. Put this in your little example thing. Wake up your neighbor if they're asleep. Okay. So 0.145 kilograms. And then the uncertainty of the velocity, I'm going to say is 0.6, because that's the range, right? So the uncertainty of the velocity is plus or minus 0.3, so it's 0.6 is the total, yeah?